Okay, let's go ahead and get started. It's 9:15, and this is new methods of fiber deployment for MDU, MTU, and other buildings. And I'm Mark Boxer. I'm with OFS. And for those of you who are in the session before this, because I think there are a few people who were in the session before this, one of the things that was discussed was how just some lessons learned with DAS deployments. And what we find is that as fiber keeps going deeper and deeper into the network, we're finding that just a lot of the tools that the industry started developing for MDU and MTU, which is what we're going to discuss here, can also be applied to other technologies and other applications such as DAS. And so what we're going to do in this presentation is we're going to start with the fiber building blocks. And so the fiber building blocks basically, you really need to have a pretty good grasp of the fiber that's being used because it really does affect pretty much everything else in the network. So we're going to start with the fiber building blocks, and we're going to spend a lot of time talking about bend-insensitive fibers and what they are and why they're important for this kind of application. Because in an MDU environment with the wrong type of fiber in the system, you basically can blow the system away with one bend. And so we're going to talk about the different types of bend-insensitive fibers out there. They can be a little bit confusing, and hopefully we'll help try and get those a little bit less confusing and simplify it a little bit. Then from that point, we're going to go through just the various portions of MTU and MDU types of networks. So we're going to talk through the head end, we're going to talk through the backbone, and going to talk about different deployment methods for that backbone, so both indoors and outdoors. We're going to do that for smaller MDUs, we're going to talk about it for larger MDUs, and then finally we're going to finish up with solutions in the living unit. So we've got a reasonably small group here, and what I'm thinking that we can try and do is if you have questions along the way, then we'll go ahead and give that a shot. If it turns out that we start getting bogged down in a lot of different questions and a lot of conversations, then I may ask to move those to the end. But if you've got questions as I go through, then please feel free and ask those, and we'll just take it from here. So I guess one thing that is new over the last 5 years is that we're taking fiber to places where it has never been before. And in order to take fiber to places we've never been before, we're also seeing a lot of just more bends and tighter bends. So outdoors, we're hearing a lot of people, especially when you get into metro areas, there's limited duct space. And when there's limited duct space, people start wanting smaller cable diameters and also smaller closures and smaller cabinets. So we're seeing tighter bends and more bends, and indoors especially. You've got fiber management challenges within the central office, and then especially when we get it inside of buildings, for a room like this or a convention center like this, if you look around, getting from one point to another may not be that simple, and you may actually have to traverse a number of different bends. And so we're seeing more and tighter bends throughout the network, and we kind of learned this as an industry the hard way, in that a lot of the first network deployments indoors had some challenges to them just because the existing loss from or the loss from existing fibers turned out to be relatively high, and you can make it all the way to a building and you're going to be fine from a power standpoint. You turn a corner and boom, all of a sudden your network is dead. So we kind of learned that the hard way, and it was highlighted by, or what actually causes this is something called macrobending. And so with conventional single mode fiber, as you go around a bend, so this is just standard single mode fiber that we've been using for the past 20, 25 years in outside plant networks. When you go around a bend, you can have enough loss to actually disrupt the service. And we'll show some of the numbers in some subsequent slides, but you can go around this corner with standard single mode fiber and basically have nothing. So the industry developed fibers that are called bend-optimized single-mode fibers or more bend-insensitive single-mode fibers. And these are actually completely different than standard single-mode fibers And we'll talk about this when we get in deeper into the presentation. It's a completely different fiber design. So it's not that you take some fibers and put a different, just a different name on it, and now they're bend insensitive. They're actually completely different fiber designs that support this. But bend insensitive or bend optimized fibers allow you to maintain the service or the service. So there is macro bending. That is a bending phenomenon, and what I wanted to do also is to highlight something called microbending. And these are completely different phenomena. So macrobending is bending that where you go around tight corners. Microbending is something where you've got a point stress that is at a location in the fiber, and that point stress causes light to go out. So the vast majority of what we're going to be talking about in this presentation is related to macrobending, not microbending. So this is a chart with wavelength on the bottom, and we've got macro bending loss on the y-axis. And with standard single mode fiber, and the standard that goes along with that is G.652D. With that single mode fiber, if you use a standard single mode fiber and you start going around a tight bend, such as what you'd see in, I'm looking for some good corners here, but like the corners in the back of this room, then you can get bend diameters down to the 5 millimeter range. And when we start seeing that, you can see losses up to 15, 20 dB. And so what this chart shows is standard single mode fiber when it's at 10 millimeters, 7.5, or 10, 7.5, and 5 millimeters. And what you'll see is that as the bend diameter gets tighter, the losses go up. And something else that's very important is that as the wavelength gets longer, the losses go up. So no matter how you slice it, as you go to tighter diameters and as you go to longer wavelengths, which are some trends that we have overall in the industry, losses go up. And so it's pretty clear that we as an industry needed to come up with something to really help to mitigate this issue. Now, something that is kind of interesting is that for a lot of fiber to the home networks, they use PON networks, passive optical networks, and the current generation of PON, so these are the various standards that are out there that support these types of networks. And for GE-PON and for GPON, these operate at 1490 nanometers, and then with some of the RF video, then you have that at 1550. And so this is the current generation. When we're putting in networks, we need to be thinking several generations ahead, because although we all kind of recognize that bandwidth demands continue to go up and electronics change, I think all of our expectation is once you put in a network, it should be around for multiple decades. And so something that we should be thinking about as we build out networks is just what does the next generation PON look like, and what are they going to be operating, and just what is the performance going to look like. And so the next generation PONs for both GE-PON and GPON are at 1577. And so if you look at 1577 versus 1490, so this is the next generation, this is the current generation, you can actually have about a 3x increase in bending loss going from one generation of PON to the next generation, because the wavelengths have shifted out. And so what that means is that you could deploy a network that's perfectly fine in an MDU today, but you go 2, 3, 5 years out and you want to upgrade this to the next generation, either EPON or GPON, and all of a sudden, instead of operating at 1490 downstream, you're operating at 1577. Your bending loss is triple, and maybe you had a dB or 2 dB or 3 dBs of bending loss across multiple bends in a building. All of a sudden, that 1, 2, 3 is now 3, 6, or 9 dB. And when you start talking about those kinds of numbers, you realize that this could be the difference between actually providing service to a customer or not providing service to a customer. So overall, the industry developed a new standard around bend insensitive fiber, and this it kind of makes people crazy because it's a little bit complicated, and what I'd like to do is try and simplify this a little bit. So the main standard is G.657. And so I mentioned earlier 652, which is for standard single mode fiber. 657 is for bend insensitive fibers. And so there are two different classifications. There is something called G.652D compliant and 652D compatible. And so these are basically the standards that are out there. There is G.657A1, A2, and B3. So really what you can take away from this is that there are really three grades of bend insensitive fibers. I think of them as good, better, and best. But what I want to do is talk about some of the real differences here. So you can see that as you go down in bend radius, then as the bends get tighter, then you go to different types of standards for the different types of fibers. So 657A1 and A2, these are typically used in, like the A1 is typically used in outside plant cables with splices and tight bends, or drop cables and micro cables. So we don't see these fibers used in a lot of the backbone cables, really because there's not that much need to use these fibers in the backbone cables. But when you get into applications like micro cables that are in metro environments, or situations where you do need to go into tighter than normal spaces, then G.657A1 really starts to make a lot of sense, as well as if you're looking at drop cables. And if we're talking about DAS types of deployments where you're doing drop cables, maybe you're going up a pole or you're going to various places and you may have to traverse some bends, then this type of fiber can make some sense in that application. The 657A2 is used in situations where you may be in a central office and you need to manage very tight bends in a central office, or you may need to manage bends in a cabinet, or you've got jumpers. And then, so this is 657A1 and A2. So I'm going to switch back, and so we've talked about these two, and these two are completely compliant with the 657 or 652 standard single mode fiber spec. So you basically can put these in pretty much any part of the network, and you can feel comfortable with the performance that you're going to get. Now there is a separate classification that is B3. And B3 was originally designed for the last drop to the home. And you'll notice, and sorry for the moving back and forth, but you'll notice that B3 is compatible and it's used with short reach applications. So this is less than a kilometer and with sharp bends. So these fibers, the standards committees decided that these fibers are really designed for this last part of the network where you're touching subscribers, and not for the central office part or the middle part of the network. And part of this is that or part of the rationale behind this is for the first 20 to 25 years of deploying networks, the actual fibers themselves kind of served as an early warning system that if you had problems. So if you're in the central office and you've got a fiber, if you're using standard single mode fiber and you've got a fiber that is bent too tightly, you'd actually have a warning about that because your attenuation would go up. And if it was too tight, then you have a lot of attenuation, and that's not a problem. One of the downsides of using this type of fiber in a central office application is you can bend these things extremely, extremely tightly. And I'll show you some examples of how you can do that. And you don't get an early warning system, because what these are meant to do is they're meant to go around very tight bends, but they're meant to do that with very low loss. So what actually can happen in situations in a very, very small number of deployments, if you go very, very tight, is you can bend these fibers so tight that actually you can see a break occur. And that's something over time. Now a break in an individual subscriber's location is, it's a problem, but it's not absolutely catastrophic. And the numbers that I'm talking about are in the low parts per million. So we're not talking about using these fibers and the network goes to pieces. we're talking about, there is a very, very small finite chance that you could have breakage if you use these in very, very tight bends. And for that reason, we don't, as an industry, really advocate the use of these kinds of fibers in the central office, because if you use this and you didn't know that there was a very, very tight bend and there was a break in a backbone type of application, that would be absolutely catastrophic for your network. So where you use these types of fibers, the G.7B3 is in the home, and so this is going to be in the home. It could be on the way to the home. It could be in the apartment unit. But the drop is the most challenging portion of the network, and it requires bending and stapling, and you really need some rugged cables and bend and sensitive fiber in this type of application. So these are designed for, as I mentioned earlier, for the drop and not for the backbone. And there is a test that's actually used to evaluate these. And it is, I don't know if there are any Verizon people in the room, but if there are, thank you very much, because this is an excellent benchmark that has been put in place for determining performance for MDU cables in a building. But the 9424 is an MDU simulation. And in this MDU simulation, you can see an example of it over here to the right. You're testing for staples, you're testing for bends, and you're testing for a weight. So you're actually putting a weight on the fiber in the context of also being in very, very tight bends. And the reason for this is if you're in a building, with a building over its lifetime, 30, 40, 50 years, is going to be contracting and expanding. So if it gets hot, it's going to expand. If it gets cold, it's going to contract. And so the weight is used to simulate the expansion and contraction of buildings, and really to look at how various components perform over time in those types of scenarios. So back to just deployments as you're going around sharp corners. This is kind of interesting because I'll ask people, what is the most challenging application for a bend and sensitive fiber? Is it stapling or is it running around a tight bend? And it's kind of interesting. These are some X-ray pictures of looking at bend and sensitive fibers. The one on the right is a staple. The one on the left is a bend. And what you see is that the bend radius for the staple is around 19 millimeters. So that's really not that aggressive in the context of what the fiber can do. But when you start going around tight bends, so if you're going around a door frame or you're going around if you're going around a corner in a building, then with this picture you're at 5.5 millimeters, and you can have some situations where you can go even tighter than that. So just a main takeaway from this is that corners overall are much more challenging than staples. So I mentioned earlier that bend and sensitive fibers are different, and they are very different in terms of the index of refraction. The index of refraction on the left is a standard single mode fiber, and you guys are probably familiar with this. It basically looks like a step. It's a step index, and some of the fiber or some of the light actually is transmitted outside of the core of these fibers. And that's been the case since the beginning of time. And that's actually why when you go around very, very tight bends, some of the light leaks out and you have significant attenuation because of the fundamental design. Now, different fiber manufacturers have different designs for bend and sensitive fiber, and it's over on the right. But something that is pretty common across all manufacturers is that these designs are more complex than single mode fiber. So you may see some valleys and some mountains and all kinds of different ways of putting together the index of refraction. So this index of these fibers are actually different fundamentally than standard single mode fibers. They're different, but they are compatible with the network. And something I'm going to show in a little bit is just kind of the overall, what is important in the network. Is it splicing or is it bending? Because in a lot of situations, I'm talking with customers and they're familiar with 0.2 dB, 0.002 dB. losses for splicing. So .02 for splicing with standard single mode fiber. So people are used to very low losses in splicing, and with some of the bend insensitive fibers, they can see numbers that are a little bit higher. And so one of the things I wanted to highlight here is that with these bend insensitive fibers, you are going to see a little bit more and different splicing performance than you would with standard single mode. But overall, in the overall context of the network, the splice loss is absolutely minuscule in comparison to the bend loss that you ultimately save. And so I'm going to give an example of that in, I think, a slide or two down the road. But one of the things I wanted to highlight was something that you can see when you're splicing bend-insensitive fibers. There is something called a gainer. And how many of you are familiar with the concept of what a gainer is? Okay, so it looks like a lot of you are. This is a situation where we're splicing just standard single mode fiber with a bend insensitive fiber. You can see that the standard single mode fiber, the mode field diameter is actually larger than the bend insensitive fiber, and an OTDR measures backscattered light. And so what we're actually measuring is light that is going backwards. So you're going to see that with the little arrows going back. And so there's actually, since it's measuring backscattered light, there's more light that is reflected at this interface, and you can end up with something on an OTDR that looks like a power gain, which is really impossible, but it's something that shows up, and it's an artifact of the way that an OTDR does its measurements. And it's not a bad thing, it's just something that you need to understand. And so, so you can sometimes see gainers when you splice these fibers, or if you're measuring in the exact opposite way, then you can see an elevated loss. So in the previous slide, I showed where it looked like a power gain, and in this situation, you're actually seeing what looks like an elevated loss. And so for the last 20 some odd years, the standards organizations have basically said, the best way to really know the actual loss is by doing a bidirectional measurement. And so that is, if you're really concerned about the overall splice loss, that's going to be the truest way in order to know the overall loss in a system. So I mentioned, and this is probably the geekiest slide that we'll show in the presentation. So forgive me for this, but it's actually important. What is being shown in this slide are basically the components of loss over the last 500 feet or so of a building. So you're running ultimately to an individual apartment, and for the last 100 meters or so, the inherent fiber loss is very, very small. But what is very important, now what we're looking at also are the performance of different types of fiber in this environment. And the reason that this is important, it just shows you the impact of bending that occurs. And this is so we've got the inherent fiber loss. This is standard single mode fiber. This is A2. So remember, this is kind of the better in terms of the bend insensitive fibers. And then the G.657A3 is the best. And so if you were doing attenuation due to bending in the Verizon drop simulation, what you would find is if you're using standard fiber in this situation, your network would absolutely go dark. If you used A2, which is the better type of fiber, and you're using it in this scenario, you could get 2 to 5 dB of loss. And then if you're using the B3, then you would have some loss, but it's going to be nowhere close to the loss that you would get if you were using the other types of fibers. Now, keep in mind that as we go to longer and longer wavelengths, that 2 to 5 can actually turn out to be 6 to 15. So the bending is extremely important. The splice loss is elevated versus what you would expect to see with outside plant, but it's nowhere close to the loss with bending. So the main takeaway from here is that when you get into an MDU and you're going into bends, standard single mode fiber won't work. If you're using the better type, then you may get away with it in the short term, but in the long term, you absolutely could have some issues from a performance standpoint. and then the G.657B3, and in this case it's the Easy Bend fiber. You would be able to actually operate the network for for today and moving forward. So in a mass deployment and in small deployments, you can absolutely get away with using the lesser grades of fiber if you're extremely careful. But if you're doing a mass deployments ultimately need ultra bend insensitive fiber to the home. So if you're going out and you're deploying hundreds or thousands of units of fiber to the home, then the ultra bend insensitive fiber really is a must in those applications. So to summarize in this part of the presentation, the central office, you'd use the A2, the feeder cables going in, and this is an overall PON network. The feeder cables and the distribution cables, you would use the A1 or the A2. In the cabinets, you typically use the A2. For the MDU backbone, where you don't have a tremendous number of bins, then you can get away with the A2. But finally, once you go into the MDU or the in-home drop, then the B3 becomes extremely important. So from here, I'm going to switch gears, and the reason I spent so much time on that portion of the presentation is that the fiber is absolutely fundamental to the deployment. I have a question.
Yeah, is the splice loss, is that actually to bend insensitive, or is that insensitive to non-insensitive?
It was, the question was the splice loss numbers that were shown, were those bend insensitive to bend insensitive or bend insensitive to single mode? And if you look at the graph, it's actually a combination. So we've got different numbers for, so the standard single mode is the G.652.
So you automatically just use the higher number, or just for your example?
Correct. Yeah, I mean, because that's kind of a worst case scenario. So any additional questions on this portion of it? From here, we're going to head into the MDU, the head end, and the closet options. And different manufacturers have different types of products. But something that's pretty key is a lot of these MDUs just lend themselves to splitter placements on site. So, in small MDUs and kind of a break-even number, or not break-even, but a rough number as far as where people typically put a splitter in versus not. I often hear the number of around 16 units. So if you've got a 16-unit building and you're using a PON scenario, then in a lot of cases you'll just bring in a fiber or a couple of fibers into that MDU, put a splitter into the building, and then go out from there. If you're dealing with MDUs that are smaller than 16, then in a lot of cases it just may make sense to just bring in fibers and basically distribute those fibers as you go through the network. But the point here is that in a lot of the MDUs, it's very, very tight spaces, and they often take the use of wall-mounted materials. So sometimes you may have rack-mounted as an option, but in a lot of cases you've got wall-mounted. Just a little tip is that you can double the capacity of a box by going with LC type connectors instead of SC type connectors. So that's just something. Overall, we see a lot of SC connectors in the network, and that's a great thing. If you are very space constrained, then LC actually has higher density, and so the LC would enable you to pack more connectors into the same size. With MDUs with higher fiber count options, then there are different types of boxes that can be used, and you can have the combination of patch splice or combination panels. So the head end in an MDU is is a lot similar, or relatively similar to the head end that what you can see in other types of scenarios. One point that I did want to make is that ribbon can be used in areas that are space challenged, and just ribbon with MPO fan outs can be a very strong space saver, and so that's something to keep in mind. And they're reasonably cost competitive with single fiber options. So that was the head end. As we start looking at some of the indoor cabling methods, we're going to go through several different methods of showing how you can actually do cabling within MDUs. And so I haven't really heard a lot of industry standard terms. So what I'm trying to do here is use just as generic of terms as I can use. And so this first method, and different manufacturers have different versions of these types of products, but a lot of them look relatively similar. So this is an MDU, and you're going down a hallway. And with the fiber breakout method, what you have is you start out and you have, instead of having an intermediate box at some location, you basically start out at the bottom of the building. You run a breakout style of cable up through the riser and then down the hallway. And then you would have some scenario where you would break into an individual fiber with this breakout cable, put a connector on it, and then attach that into the in-unit cabling system. So this is pretty effective for, and so this is kind of showing the in-unit cabling system. This is pretty effective for smaller MDUs. It can be used with some of the larger ones, but you've got to have a lot of space in the riser in order to be able to deploy a number of these types of cables. So this is how you actually break it out. It uses the breakout style of the cable. You can add a mechanical splice-on type of connector. And what you're doing is you open up a couple of windows in the sheath. So we're showing that process with these pictures, where you're basically opening up a couple of windows in the sheath. So you've got one window right above the doorway. You've got another window that's maybe a foot or two away, or 2 or 3 feet away. And so you open up the cable sheath, you cut the fiber that you want a little bit farther away from where the door is, and then you pull the fiber back, you add the connector, and you plug that into the network, and then from there you can run the cable inside of the home. So this is this is one of the styles, and actually this, when you look at this for a small MDU building, then both from a material standpoint and a labor standpoint, this is actually a relatively cost-effective way of doing things, because the materials are relatively small. The labor, there's no intermediate splicing or connectors that are used, so you're basically just you have a connector at the head end, which we're showing down in the bottom left, and then you have a connector right at the doorway where you go ahead and load in a customer, and that's really it from a deployment labor standpoint. So this can be a very cost-effective way of deploying in smaller MDUs. So this is so the first method is the fiber breakout method. Another method of deployment is I call it using classic cables and enclosures. So in this situation, what you do is you would run a number of cables up to a floor, and you would have an intermediate connection box that is used, and then from that point you run out drop cables down the floor. And so you've got various components here. You've got riser cables, enclosures, and drop cables. And this is also a very cost-effective way of deploying, primarily from a material standpoint. But when you get into the labor for this, the labor can be a little bit more, because you could potentially have connectors here at the head end, connectors or splices here at the intermediate location, and connectors or splices back at the customer location. So although the materials for this type of deployment can be very low, the labor actually can be a little bit higher. So those are a couple of methods to use in smaller MDUs. One of the methods also that you can use, and those are both indoors. Now, what about those situations where there really are no paths that you can go indoors? So there are a lot of buildings with very crowded risers or no risers whatsoever. And so how do you deploy in those types of scenarios? And there are actually methods to do, and I'm going to show one here, and that's an outdoor cabling method. So sometimes there's not a fiber path that's actually available indoors because you don't have riser space. Maybe the building says, I just don't want your guys inside and interrupting our clients as they're going through their daily lives. So some of the advantages of outdoor installations, it can be a very fast, easy installation. You don't need bin limiters, conduits, or raceways. And then the installation for this could be done in either a horizontal or a vertical type of configuration. Now, the main drawback for this type of scenario is you've got a cable or series of cables on the outside of a building. And a lot of building owners would be sensitized to that and not want to see the cables on the outside of the building. So for all these methods, there are various pros and cons. And you should consider them to be various, really, tools in the toolbox as you go to deploy. Just note that you've got a lot of different types of tools that can be used. So for the outdoor method, something that it can deploy very, very quickly, because basically all you're doing is you can either feed down or feed up, but you're basically just dropping a cable down the side of a building. You're securing it at a couple of different points, and once a customer looks to sign up, then all you do is you've got a connector, you've got a tie wrap that's on the connector. So basically these are bundles of individual cables that are spaced on the outside of the building. So you've got a bundle outside. Once a customer is looking for service, they call up, and then you just grab the bundle, you clip the tie wrap, pull out the connector, and then drill a hole, and then insert that through the hole in the home, attached to the ONT, and you're ready to go. So it's actually a very fast installation. It's a very cost-effective installation when you look at it from both materials and a labor standpoint. But this is a situation where you really have to work with the building owner and know what the building owner wants to do and make sure that they're comfortable with this approach. So those are some solutions for smaller MDUs, and larger MDUs can require specialized equipment. Now, for larger MDUs also, especially if they're older, they don't have a lot of riser space. And if you don't have a lot of riser space, then ribbon cables can actually be very effective for backbones because it just minimizes the number of individual cables that you have, and it minimizes the riser space that they take up. And also for larger MDUs, pre-connectorized solutions really can be a very strong key because it enables you to deploy a lot faster than if you're going and splicing in all the connections into a larger building. So in this scenario, we're showing a different type of solution where you've got cables that are going up from the riser location, and these are ribbon cables. And there is an intermediate, this is actually an intermediate combiner. And so it basically pulls all the fibers together and combines them into an intermediate point. And in this scenario, you can do 60 to 72 customers. So if you've got roughly 12 customers per floor, then one of these guys can be placed every 5 or 6 floors, and you put it in the middle, and then you can run individual drop cables down each floor, or hit 3 or 4 floors for these individual combiners. Actually, they feed into a terminal, and the terminals actually go on each floor, and then you go from the drop cables. I forgot to include the terminals earlier. But so you have the head end, it goes to a combiner unit, it goes to an individual terminal that goes to each floor, and from the individual terminal, you go to each individual unit. And so the advantage of something like this is you're packing a whole lot of fibers into a small space. And so you're using up not very much riser space, and also from an installation standpoint, you can install these very quickly because everything's pre-connectorized. There is a ribbon cable on the end of all these terminals, and so you just plug those into these combiners, and then the drop cables can be pre-connectorized, or connectorized on one or both ends, and you just run those the drop cables back into these terminals, and so you've got a pretty simple installation. So looking at using like the classic system that we talked about earlier, where you have individual boxes on each floor versus a plug-and-play type of system, what you'll find is that the plug-and-play can actually use just a lot fewer numbers of cables, fewer terminals, fewer splices, fewer riser diameters, and a smaller amount of labor. So again, for all of these, you've got different options for the different types of materials that you can use, and there may be some situations where you are worried about minimizing material costs, and some situations you're worried about minimizing labor costs. Some situations you may not have a lot of access to risers. So you just look at, all MDUs are different, so you've got to look at the various tools in the toolbox and pick out what makes them the most sense. So these are some pros and cons of the various solutions. And so I'll toss those up. I'm not going to go through these in a tremendous amount of detail. And from here, I want to go ahead and start to close by talking about some of the in-unit solutions. And something that is key when you get into the unit, MDU homeowners are very sensitive to cable deployments within the homes. And we've seen this now on multiple continents. So multiple customers on multiple continents, and the customer absolutely ultimately dictates the terms inside. So outside, as a service provider, you can go in and say, I need big things, and I need to be able to manage bins. Inside the home, the customer ultimately is the boss. And we've heard anecdotally that anywhere from 5 to 10% of customers will refuse service just based on the aesthetics of the cables that are in their homes. And so, we've got the little baby who's not too happy about that. But the main point here is that in a lot of situations, especially in some of the higher end communities, people are just very sensitive to the aesthetics. And also the in-unit pathways can be very challenging because the customer may say, I want the ONT in the study out of the way. And so this is a hypothetical apartment building. You're coming in the doorway, and if you follow the various bins through this, you end up with one bin coming in, 2, 3, 4, 5, 6, 7, 8, 9 bins in order to actually locate the ONT in the study where they wanted the ONT to be. And so 9 bins. Going back to the very beginning of the presentation, we talked about the importance of bend-insensitive fiber and why it really is a necessity for mass deployments. So this is an example where that really comes in. But there are many ways to actually deploy within the unit. Clearly, new construction before the walls are put in place. This is absolutely the best case scenario. In the U.S. and actually in a lot of places around the world, until this past year or so, we haven't seen a tremendous amount of new construction. One of the things that I've been, a little bit heartened about over the past couple of months is I'm now starting to hear again about some new construction. But new construction is a very favorable scenario because you don't have the aesthetics concerns. So, you've got a couple of different ways you can do this. You could do microductor cordage, and, this is good acceptance, medium installed cost, reliable service. You can use the G.7 607B3 fiber that we talked about. There are a couple of different flavors of that, and you can have that stapled in place. That's good acceptance, low installed cost, and reliable service. But both of these are inside the walls, and you do that before everything is done. So those are very favorable scenarios. Now, with existing construction, then that gets a little bit more challenging, especially with aesthetic concerns. So with stapling, you've got a couple of different ways of doing this. One is just stapling the 657 fibers that we talked about earlier. There are some customer aesthetic concerns here. You have low installed cost and certainly reliable in service. Mini tape is another option, and you could have some customer aesthetic concerns, with that as well. There's also now a new type of deployment that's a mini cord, And the mini cord has actually had pretty good acceptance over the past year, and we've seen these come out over the past year to 18 months or so. And with the mini cord, it basically is, it's just very, very small, and it's deployed in a way that makes it very unobtrusive. And so it also has just a relatively fast installation. And so this is a method that we're seeing a lot of take up, in the past 12 to 18 months. There are components for this solution. You've got a 900 micron buffer tube or buffered fiber. You've got an adhesive cartridge. You've got various bin limiters that can be used just to manage the bins. If you need to drill holes through the wall, which is almost guaranteed you're going to need to drill holes through the wall, you'd have through the hole kit. And so that pairs the tool in order to take a connector through the wall plus hole covers to cover everything up. So, so ultimately what you end up with this scenario is an installation that is very unobtrusive. Some situations we've heard of customers who actually want to take these down hallways as well. So it's it's an interesting application, and it's something that's relatively new over the past 6, 12, 18 months. So that is the end of the formal type of presentation. I'm going to toss up a couple of slides about OFS as a company if you were not familiar with who we are. And then finally, just from a summary standpoint, there are a wide variety of new technologies to support MDU deployments, but the main reason we went through the introduction to the fiber is that bend-insensitive fibers really are the main building blocks in order to make MDU and MTU deployments occur. The 657B3 fiber is an integral component for the drop. You've got a number of different types of solutions going to the unit, some indoors, some outdoors. The Breakout, the classic type, the spool and play, and different manufacturers have different versions of these, as well as the solutions in the unit. Different manufacturers have different versions of these types of products as well. So from here, I'm going to open it up again to any additional questions. Yes, sir.
Is it safe to assume that micro cord is that B3 fiber?
Absolutely. Absolutely, yeah. No, the question was, is it safe to assume that the microcord uses G.7 B3 fiber? And the answer is absolutely, because really, as we discussed in the early part of the presentation, there really would be no way that if you used it with a different type of fiber that you would have effective transmission, number one, through the bins, and then number two, through the generations of equipment that operate at different wavelengths. Correct. I think different manufacturers could do different things. Maybe we could have a discussion afterwards, at least for some of the components that my company can do. Additional questions? Yes, sir.
With using high-powered lasers now, are there any issues with the connector types used with the different fiber types? So when you go into G657, are there any power issues, power handling issues?
That is an excellent question that I have actually never been asked before. So the question is, with the use of higher powered lasers and a lot of the bends that are occurring in networks in the MDUs, are there any concerns about that combination? So I think it's an excellent question. I'm going to give you a very unrehearsed answer because it's the first time I've had the question, and I would say that at least at this point, with everything that's on the table, we have not seen or heard of any types of those kind of scenarios that we should be concerned about. With higher powered lasers, you do run into some concerns as far as the amount of power, and can you damage the glass? Can you damage the connector components and those kinds of things? I believe that we are well below the threshold where any of those kinds of interactions can occur. but I think it's, and we certainly have not seen any of those kinds of interactions that have occurred with any of the deployment scenarios to this point. I'm going to give that as a qualified response because, frankly, it's the first time I've had the question, and so I haven't studied it in detail. But I think we are well below the threshold where we would actually have any significant concerns about it. Any additional questions? Yes, sir. So let me paraphrase that question and make sure I got it right. So the question is, with a lot of the fast Ethernet deployments, are we seeing these types of issues around those types of deployments? I mean, is that and what I would say with that is fiber now is going to a lot of places that has never gone before, and so it is. In some of those cases, that could be residential service. In some of those cases, that could be business service. Businesses can operate in the same types of strange environments that residences operate. And so, I guess part of the answer is that these types of issues would be protocol independent. So, regardless of whether it's PON type service or Ethernet service over PON, you could absolutely run into these scenarios because they're basically they're around where the fibers are ultimately going. So if you've got a customer that is using fast Ethernet service and they're in a renovated warehouse and you've got to get from point A to point Z in that renovated warehouse, then you absolutely could run into these types of scenarios. And these scenarios really are they're not protocol dependent, so it doesn't matter if it's ATM or Ethernet or PON. It's basically the function of the light traveling down the fiber. Does that answer your question? Additional questions? These are all fantastic questions. Well, thank you all very much for coming. I really do appreciate you coming and listening and asking great questions. I'll stay up here for a little while if you have any additional questions. Also, please come by and see us at the booth. It's 7:31.